Hello everyone. On this video we will be looking at limits at infinity. Alright, so what that means is that this will discuss the end behavior of a function on an infinite interval of a function on an infinite interval. Okay, so that means that x won't be between some a value and b value. X will just keep getting bigger and bigger and bigger forever and ever, or it'll keep getting smaller and smaller and smaller forever and ever. Okay, so to kind of give you an idea, let's show you this example. F of x equals 3x squared over x squared plus 1. Okay, we want to see it as x approaches positive infinity and the value as x approaches negative infinity. So as x keeps getting bigger and bigger and bigger and x keeps getting smaller and smaller and smaller, exactly what value, well, limit value you have for this function. Okay, so to do that, we're going to go to the old trusty table here. Okay, so this is your x value, and don't really need it that big. And this is your function of x. Okay, so let's say if we start at 0. Okay, so if you plug in x equals 0, you'll get 0 over 1, which is 0. Okay, so if you plug in x equals positive 1, you'll get 1.5, or 3 over 2. You plug in x equals 10, you'll get 2.97. You plug in x equals 100, you'll get 2.9997. And if you keep on plugging numbers bigger and bigger and bigger as you get closer to infinity, you just keep getting closer and closer and closer to the number 3. Alright, so what if we go towards negative infinity? If you plug in negative 1, you will still get 1.5. If you plug in negative 10, you will get 2.97. If you plug in negative 100, you will get 2.9997. Okay, so as this number keeps getting smaller and smaller and smaller, or approaching negative infinity, your f of x gets closer and closer and closer again to the number 3. Okay, so we see here x approaches infinity this way, and x approaches negative infinity this way. Alright, so if you were to sketch this function, it would look something like this. And let's say this is our x-axis, so you have our x-axis and your y-axis. Okay, so this graph will look something like this. So let's say this is your f of x equals 3 or y equals 3. And we put this just above here. This graph will look something like this, where it will just get really close to 3, but it'll never touch it. Same way here. This is going to get really close to 3 as x gets bigger, but it'll never actually hit 3. It's just a limit of 3. And this one, as you get smaller and smaller and smaller, this number will get closer and closer and closer to 3 without actually crossing it. Okay, so in this case, y equals 3 is your horizontal asymptote. Of f of x equals f of x, let me move that down a little bit, of f of x equals 3x squared over x squared plus 1. Alright, so which brings us to our definition of a horizontal asymptote. Okay, so the line y equals some limit L is a horizontal asymptote of the graph f of x if 1, the limit of that function as x approaches infinity equals L, or the limit of that function as x approaches negative infinity equals that limit L. In this case, your L is equal to 3. Okay. Now, this is just one case. It does not have to be both. This is just one case where it's both of them, but both of these do not have to have that vertical asymptote. It could just be one where it comes from negative infinity and goes up like that. Okay? Does not have to be both. Just a little side note there. Alright, so if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next page. Straighten that out. There we go. Alright, so let's say if we know that a variable r is a positive rational number. And we know that some variable c is any real number. Oh, little comma. then that tells us that the limit of some constant c over x to the r power as x approaches infinity equals 0. Or the limit of some constant over x to the power of r as x approaches negative infinity equals 0. Alright, so I'll explain why that's the case on our example. Okay, so let's say, for example, we want to evaluate the limit. Okay, so the limit as x approaches infinity of 5 minus 2 over x squared. Alright, so remember from your limit rules or limit laws, you can go ahead and distribute that limit to both of those terms. So that gives you the limit of 5 as x approaches infinity minus the limit of 2 over x squared as x approaches infinity. Okay. Now we already know that the limit of a constant, it doesn't matter what it's approaching. The limit of a constant is just that constant. So that's going to be 5. Minus, now this is where our little rule up here comes in. Here you have 2 over x squared. Okay, and this x is getting bigger and bigger and bigger. So let's say you have 2 over 10 squared. So you have 2 over 100. Okay. What if x is now 1,000? What if x is 10,000? What if 100,000? What if it's a billion? What if x is a trillion now? X is getting bigger and bigger. So you have a trillion squared. So you have 2 over a trillion squared. Now it's not 0, but 2 over a trillion is really, 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 really close to 0. And it's just going to keep getting bigger. Okay, so you have that constant over x raised to the power of a real number, or a positive rational number. So we know that the limit of 2 over x squared is just 0. So 5 minus 0 is 5. So the limit of this whole function is 5. Alright, so let's try our next example. What if we wanted to evaluate the limit? Okay, so if that's the limit of 2x minus 1 over x plus 1 as x approaches infinity. Okay. Now, if you just tried plugging in infinity, you can't really do it because you have 2 times infinity minus 1, which is still pretty much infinity, over infinity plus 1, which is still pretty much infinity. So if you try direct substitution and just plugged in that infinity, you get the limit as x approaches infinity, 2x minus 1 over x plus 1, which is just infinity over infinity, which doesn't tell you a thing. This is actually an indeterminate form, which we will cover later. Okay, so you end up with infinity over infinity. Can't do anything with that. So what we have to do is we have to kind of manipulate this one a little bit. Okay, so how do we do that? Well, one way is divide the numerator and denominator by the lead variable. In the denominator. Okay, so your lead variable in the denominator is x. So that means the limit, let me bring this up some, here we go, as x approaches infinity. So you have 2x, we're going to divide each and every term by x. So you have 2x over x minus 1 over x over x plus 1 over x. Okay. Now we see here the 2x's cancel out. So we're going to go ahead and write the limit as x approaches infinity of 2 minus 1 over x over x here is just 1 of 1 plus 1 over x. Okay. Now we can see here, if we distribute the limit to the numerator and denominator, the limit of the constant 2 is just, well, might as well go ahead and write it out. The limit 2 minus 1 over x, as x approaches infinity, over the limit of 1 plus 1 over x. There we go. So if we distribute that limit to both of those, move my equal sign over, that's going to equal the limit of a constant is just that constant. So you have 2. And remember, the limit of a constant over x, this is just x to the first power, is going to equal 0. So you have 2 minus 0 over the limit of a constant, which is 1. The limit of 1 is just 1, plus the limit of 1 over x, again, is just 0. Okay, so you have 2 over 1, which is 2. Okay, so you can always manipulate your function, okay, to make it to where it's a little easier to work with. All right. So if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. All right. So what if we wanted to find the limit? Okay, so the limit as x approaches infinity of 3x minus 2 over the square root of 2x squared plus 1. Okay, so once again, if you plug in infinity, you can see that won't do anything. So if you use direct substitution, the limit 3x minus 2 over the square root of 2x squared plus 1 as x approaches infinity, you just end up with infinity over infinity again, which is your indeterminate form, which you can't do anything with. Alright, so what do? Well, you do the same thing here. You look at the lead variable in your denominator. Alright, so you want to remember that x is equal to square root of x squared. The square and the square root cancel each other out. Okay. Why is that important? Because we're going to divide each one of those terms by square root of x squared. Okay, so that gives us the limit of 3x over square root of x squared. Remember, square root of x squared is just x, so I'm just going to write that as x. Minus 2 over square root of x squared, which again is just equal to x, over, let me write that limit a little bit, or even, there we go, over, you have the square root 2x squared plus 1 over square root of x. Oh, square root of x squared. Sorry about that. And let me make that 2 a little bit bigger. Over square root of x squared. There we go. That's a little better. Oh, as x approaches infinity. Alright. Now, we go ahead and simplify each one of those. Limit as x approaches infinity. The x's cancel out, so here we just have 3 minus 2 over x divided by, when you have a square root divided by a square root, you can just combine them under one umbrella root. So if you have square root of m over square root of n, you can just make that the square root of m over n. So we're just going to put those under one big square root. So that's the square root of 2x squared. Let me make that a little bit bigger so it fits nice and neat. Of 2x squared plus 1 over x squared. Alright, so nice and neat, all under 1. Okay, so now we're going to go ahead and just separate those two. So you have the limit as x approaches infinity of 3 minus 2 over x over square root, make that a little bit bigger, 2x squared over x squared plus 1 over x squared. Okay, so we distribute that limit using our limit properties to both the numerator and denominator. We have the limit as x approaches infinity of 3 minus 2 over x over the limit as x, move that up, there we go, as x approaches infinity. Here you see the x squares cancel each other out. That's why you pick that from the beginning. Those two cancel out, so that's just the limit of 2 plus 1 over x squared. And again, once we distribute those, we can go ahead and solve. So the limit of 3, the limit of a constant is just that constant, so that's still going to be 3. Okay, now the limit of 2 over x, x is just going to keep bigger, so this is just going to get closer and closer to 0. So minus 0 over the limit of 2 is just 2. And you have 1 over x squared. Remember that x squared is just going to keep getting bigger and bigger, so it's getting closer and closer to 0. Oh, forgot my square root. Sorry about that. So actually this should be square root 2 over 0, 2 plus 0. Alright, so that gives us 3 over square root of 2, or multiply the numerator and denominator by square root of 2 to rationalize the denominator, and that's 3 square root of 2 over 2. Alright, and that would be your answer for this one. Alright, so if you are still writing, feel free to press pause. But now we're going to look at solving polynomials when they're approaching infinity. Okay, so polynomials at infinity. Okay, now with this one, this is a very important hint. For limits of a polynomial as x approaches either positive or negative infinity, just focus on the leading term. Okay, and I'll tell you why when we do our first example. Okay, this will just make it go by so much easier. Okay, so let's say, for example, move that up. There we go. There we go. Let's say if we want to find the limit and that's the limit of negative 2x squared plus 5x minus 10 as x approaches infinity. All right. So what we're going to do is we're just going to focus on the negative 2x squared. Because if this is a really big number squared and then doubled, it's not going to really matter much that you have 5 times that number. So if you have a trillion squared and then multiplied by negative 2, that's a humongous number. If you have 5 times 1 trillion, that 5 trillion is not going to mean anything when you have a ridiculously big number like that. That's just getting bigger and bigger. So because this number here, or this term, is kind of what directs the entire function, that's the one we're just going to focus on. Okay, you don't have to focus on the other two, just focus on the lead one. Okay, so we have the limit as x approaches infinity of negative 2x squared and plus, and we don't even worry about the rest. Okay, so now we look at the behavior of this one term. Okay, so x approaches infinity, what does that tell us? X approaches infinity just means that x squared is a really big positive number. Okay, so x is just getting bigger and bigger and bigger, so x squared is just a really big positive number. Okay, now why is that important? Because negative 2x squared means you have a positive x squared multiplied by a negative 2. Okay, so you have that big positive number multiplied by a negative number. That just gives you a really big negative number, because a positive times a negative is negative. This gives us a really big negative number. So let me clean up that a little bit. There we go. Okay, so when you have a really big negative number, that's just a number that's just going to keep getting bigger and bigger and bigger and bigger in the negative direction. So that means it's just going to approach negative infinity as x keeps getting bigger and bigger and bigger. Okay, so that means the limit of negative 2x squared plus 5x minus 10 as x approaches infinity is just going to equal negative infinity. So, leave that up some. Okay, so that's why you focus on just the lead term when dealing with a polynomial. Okay, it directs the entire thing. It's calling the shots on this one. All right. So if you're still writing, feel free to press pause, but we're going to go ahead and move on to our next example. Okay, so let's say, for example, we have the limit as x approaches negative infinity of negative 4x to the fourth power plus 2x to the third power minus x squared plus 4x minus 2. Okay, so we want to find the limit of that one. All right, so once again, we just worry about the leading term. Okay, so we have the limit as x approaches negative infinity of negative 4x to the fourth power plus blah, 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 etc., and so on. Okay, again, this is the one that's leading the direction. All those others eventually are going to be so much smaller than this lead one. So this is the one calling the shots. Okay, so what does this tell us? Just by this lead term. Well, x approaches negative infinity is just a really large negative number let's just keep getting smaller and smaller and smaller and smaller and smaller. Okay, so if you have that negative number raised to the fourth power, what does that do? X to the fourth as x approaches negative infinity is just a really large negative number. Move that up. Raised to the fourth power. Let me clean up that R. There we go. Raised to the fourth power. So you get any negative number raised to the fourth power. Think about negative 2. Negative 2 times negative 2 times negative 2 times negative 2 is positive 16. Okay, so same thing here. If you get any negative number, because remember, this is just getting smaller and smaller and smaller in the negative direction. You raise that to the fourth power, it becomes positive. Okay, remember, any negative number raised to an even power is going to be positive. A negative number raised to an odd power is going to be negative. Okay, so you have that positive number, x to the fourth is going to be positive, even as this number is negative. Okay, so now you're going to get that positive x to the fourth and multiply it by negative 4. So you multiply x to the fourth as x approaches negative infinity by negative 4. Okay. All right. So what you have here is you have a really large positive number multiplied by a negative number. To get a really large positive number, multiplied by negative 4. So if you have a positive times a negative is a negative number. Large negative number. Or in this case, that number is going to keep getting smaller and smaller, so you just call that negative infinity. So that tells us that the limit of negative 4x to the fourth plus 2x to the third minus x squared plus 4x minus 2 as x approaches negative infinity is equal to negative infinity. Alright, so that's kind of the thought process on that one when you're dealing with polynomials. Okay, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. Okay, so if you want to find the limit, okay, so let's say you have the limit of negative 6x to the third minus 2x squared minus 4x plus 5 as x approaches negative infinity. Oh, there we go. Now, what I want you to do is I want you to press pause and try to work this one out on your own. Alright, so I'm assuming you've pressed pause and you worked this one out. So let's go ahead and verify your answer. Remember, you're just working on the lead coefficient. That's all you're using because that's spearheading everything. So it's really just the limit as x approaches negative infinity of negative 6x to the third plus blah 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 or minus blah blah blah. It doesn't matter because we're kind of ignoring the rest of those. Okay, so we know that negative infinity equals a really large negative number. Okay, now if you get that really large negative number, or really, I guess you can call it really small negative number, large in quotes because it's a large absolute value, but still a negative number, so it's really, really small. Okay, so that means you have x to the third power What is that? Well, that's just a really small negative number. Well, I guess you get really large. Again, large is in quotations because technically it's a small number, but because it's getting smaller and smaller, it's really to be negative billions and trillions, I'll put large in quotes. Negative number raised to the third power. Okay. Now you get a negative number raised to the third power, it's still negative. Think about negative 2. Negative 2 times negative 2 times negative 2 is negative 8. So a negative number raised to the third power is still negative. So this is still negative. Okay, so you have that negative, really big negative number, and you're going to multiply that really big negative number times negative 6. Okay. They're really, again, large is in quotes. Negative number multiplied by negative 6. So you have a really large negative number multiplied by a negative number. That becomes a large positive number. Okay, so that large positive number is just going to keep getting bigger and bigger and bigger. So that becomes basically positive infinity. So we know the limit of negative 6x to the third minus 2x squared minus 4x plus 5 as x approaches negative infinity is equal to positive infinity. Most of the time you don't need the plus sign, but I'll just put that there anyway. All right. So if you are still writing, feel free to press pause. We're going to go ahead and do a few more examples. All right, so let's say, for example, we want to find the limit, problem A. We have the limit sine of x as x approaches infinity. And for problem B, we have the limit of 4 times tangent of 1 over 4x plus 1 as x approaches negative infinity. Oh, move that over. There we go. Alright, now, one thing you need to know about sine and cosine oscillates between -1 and 1. They basically both have just that kind of shape. So there is no limit. You have a function that just oscillates between two numbers, bounces back and forth. It doesn't approach any one value. It bounces all over the place. So, quick note, as x approaches infinity, f of x equals sine of x just oscillates between -1 and 1. So in this case, the limit does not exist. So the limit does not exist. That is actually your answer. It does not exist. Or in most cases, it would just be D N E. Alright, so that's problem A. Remember, the same thing for cosine. If you have the limit of cosine as x approaches infinity, it's just going to bounce back and forth. Now, if it was approaching a particular value, that's different. You can actually find the limit as it's approaching a particular value. But if it's just approaching infinity or negative infinity, it's not going to exist. Alright, so for problem B, move that up. There we go. Alright, now for problem B, you want to look inside of there first. So you have the limit. Well, actually, before we write down the limit, one thing you want to do is notice that 1 over 4x plus 1, it approaches 0 as x approaches negative infinity. As x approaches negative infinity. Okay, so as x gets smaller and smaller and smaller, well, a negative number, you get 1 over negative whatever. And it's getting, that x is getting bigger and bigger and bigger. So 1 over 4 times negative a billion is just going to be really, 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 really close to 0. Okay, so what we can do is we can factor out our 4. So we now have 4 times the limit as x approaches negative infinity of tangent 1 over 4x plus 1. Okay, so you can actually take this and have just the limit of what's in there. So that becomes 4 times tangent of the limit of 1 over 4x plus 1. So 4 times tangent. Let me kind of clean that up so I'm not skipping any steps. 4 times tangent of the limit of 1 over 4x plus 1 as x approaches negative infinity. So this gives us 4 times tangent. Remember, the limit of that is 0 as x approaches negative infinity. So you have 4 times the tangent of 0. Tangent of 0 is 0. So you have 4 times 0, which is just 0. Alright, so you can manipulate your trigonometric limits also. Alright, so if you are still writing, feel free to press pause, but we're going to go ahead and do one more example. Okay, so what if we wanted to find the limit sine of x over x as x approaches infinity? Okay, now this is different than just limit of sine of x. Okay, so you have sine of x over x. Okay, so I'm going to show you how to solve this using the squeeze theorem. Okay, so we already know that sine of x is going to oscillate between -1 and 1. So it's going to be -1 and 1. It's going to oscillate between those two values. So now what do? We divide each one of those values by x. Okay, because really we want our middle term to be this. Okay, so if you had cosine of x, you'd start off with cosine between -1 and 1, then you divide by this. Even if it was x squared, then you divide it by x squared. Same thing. Or if it was multiplied by another value, then you just start with this, then you'd multiply by that value. It works the same way. Okay, so now we divide by x. So that gives us -1 over x less than or equal to sine of x over x is less than or equal to 1 over x. Okay, so we do the same thing to each section. Alright, so now we apply the limit to each section. Okay, so we have the limit of -1 over x as x approaches infinity, so we use the same one up there. As x approaches infinity, less than or equal to the limit as x approaches infinity sine of x over x, less than or equal to the limit as x approaches infinity of 1 over x. Alright, so now we just do the 2 on the outside, and using the squeeze theorem, that should give us the limit of the inside. Okay, so we know the limit of -1 over x, as x keeps getting bigger and bigger and bigger, this just keeps getting closer and closer to 0. So that gives us 0 less than or equal to the limit of sine of x over x as x approaches infinity, which is less than or equal to the limit of 1 over x as x approaches infinity is again 0. So if this limit is 0 is less than or equal to the limit and greater than or equal to this limit, then the only thing it could mean is this limit is equal to 0. So by the squeeze theorem, the limit sine of x over x as x approaches infinity is equal to 0. Okay. Now remember when I said that on the previous page, excuse me, I'm just going to cover this for 1 second. The limit of sine of x is not the same as the limit of sine of x over x. The fact that it oscillates only is a rule you can only use for limit of sine of x and the limit of cosine of x. When it's something different like that, then you use the squeeze theorem, and that helps. Alright, so hopefully this all made sense, and I will see you on the next video.